Jai Hind, myself Neha Garg, and the subject is the fundamental of electronics engineering. Today the topic is the operational amplifier. So basically, what is the operational amplifier? Operational amplifier is a high gain directly coupled difference amplifier, and it consists of multi stages. Like differential amplifier, it is made up of BJT, common emitter configuration, like in this way. This is the diagram for the differential amplifier. Like this is V1 and this is V2, and here there will be output. If we will see the operational amplifier, the diagram, the symbol of the operational amplifier is in this way. This is for the non-inverting input, and this is for the inverting input, and this is for the output. Inside this triangle, there are so many differential amplifiers which are made up of these BJTs. Differential amplifier may be of 4 types, like dual input, balanced output, and dual input unbalanced output, single input balanced output, and single input unbalanced output. If we are applying both inputs at this input terminal and taking output at both the terminal V01 and V02, then this is called the dual input balanced output. And if we are applying both inputs but we are taking the only one output, then it is called the dual input unbalanced output. And if we are apply the single input and taking single output, then it is called the single input and unbalanced output. And if we are applying single input and taking both output, then it is called the single input balanced output. So in this case, in this triangle, we are using different differential amplifiers. In first stage, dual input balanced output is used, and in second stage, dual input unbalanced output is used. So, and the gain of these differential amplifiers cascaded, and the overall gain of this operational amplifier becomes very high. So basically, this operational amplifier is a high gain directly coupled because it consists of multiple stages, and at each stage there is a differential amplifier is there. So all these differential amplifiers, all these stages are cascaded with the direct coupling, and this is a difference amplifier. Difference amplifier means it amplifies the difference of the two signals. Like this is V1 and V2, and the difference between these two signals is V1 minus V2. So this difference will be amplified by this op-amp. So that's why it is called as a difference amplifier. Like BJT in BJT common emitter configuration is used as a amplifier. But here we apply the input signal and we are getting the output signal here. If the input signal is in this way, in case of common emitter configuration, this output will be 180-degree phase shift. So BJT amplifies the only single input signal, and op-amp amplifies the difference between the two signals. And the advantage of this feature is that it rejects the common mode noise. If the noise is applied at this end, like this is the noise VND, and noise is applied at this end, that is the VND. So overall gain, if we will see, this will be A times of V1 plus VND minus V2 plus VND. So we can see this VND will be cancelled, and output will be A times of V1 minus V2. So by using this feature, that difference of the two input signal will be amplified, we can reject the common mode noise at both ends. So this is the advantage of this operational amplifier. And why it is called as an operational amplifier? Because it performs the different mathematical operations. Like we can design subtractor with the help of this. Subtractor means if we apply two voltages at the input terminal V1 and V2, then output will be the subtraction of these two voltages, V1 minus V2. And we can design any adder with the help of this operational amplifier, log amplifier and anti-log amplifier, and like integrator, differentiator. So many mathematical operations can be performed with the help of this operational amplifier. That's why it is called as the operational amplifier. Now we can see this is the symbol for the operational amplifier, and this is the pin number. This is the non-inverting input, plus is the non-inverting terminal, and minus is the inverting input. If we want to make a inverting amplifier, then what we have to do? We have to apply the input signal at the negative terminal, and this terminal must be grounded. And if the gain of this amplifier is A, in that case, output would be equal to minus A times of V1. This is in the case of inverting amplifier. And if we want to make the non-inverting amplifier, we will ground this terminal and we will apply input at this terminal. And in that case, output will be equal to V0 A times of V1. So we can say in case of inverting amplifier, when we design any inverting amplifier, then the output, if the input was in this way, output will be in this way. For 180 degree phase shift will be this, like in this way, and this will be like in this way. And if it was for the case for the non-inverting amplifier, input is this, so output will also be this. 0 degree phase shift will be there. And this is the pin IC 741 that is used for the op-amp, and it is a 8-pin IC in which 7 pins are functional and 4 pins are input pins and 1 pin is the output pin. So here pin number 6 is the output pin, and pin number 2 and 3, pin number 2 is the negative inverting input pin, and pin number 3 is the non-inverting input, and pin number 4 it is connected to the minus VCC, that is minus 15 volt, and this is the plus VCC, that is plus 15 volt. So these are the pin number 4 and 7 are used for providing biasing to the IC. If we are not giving these biasings to the IC and we are applying input at terminal 2 and 3, then the output will be 0 because there is no biasing given to the IC. So first of all, if we are performing any practical for the op-amp like subtractor, integrator, differentiator, we have to give the biasings first. Here we have to connect the minus 15 or minus 12 volt here and plus 15 or plus 12 volt here. And then we can, if we want to design the inverting amplifier, so in that case, we will ground this terminal and we will supply to this terminal inverting input and biasing through this pin number 4 and 7. And in that case, output will be at this point, pin number 6. Pin number 1 and pin number 5 are the offset null, and these offset nulls, they are given for if like in the case of the op-amp, if we are applying ground, V1 and V2 both are 0, inputs are 0, then output must also be 0. But it does not become 0 because the transistors that are used in this op-amp, these transistors are not perfectly matched, and due to which if V1 and V2 both are 0, there will be output voltage at the output terminal, and that voltage is called the output offset voltage. So to nullify that voltage, we apply some voltage at the input terminal. That voltage is called the input offset voltage. So these offset nulls are basically used for making the output offset voltage 0. And these diagrams are for the non-inverting amplifier and inverting amplifier in open loop configuration. Open loop configuration means we are not applying any output to the input. There is no feedback from the output to the input. So this is the case, minus is grounded and supply is given at the positive terminal. So this is the non-inverting amplifier, and there is a 0 phase shift is there, like signal is this and output is also this. And here this is the inverting amplifier, Vi is applied at the negative terminal and plus terminal is grounded, and we can see there is a 180 degree phase shift is here. So this is the open loop configuration where we can make the non-inverting and inverting amplifiers. After that, virtual ground concept. So virtual ground is basically a node in a circuit which is at ground potential, but it is not physically connected to the ground. Like we can see this circuit. So we can see here. So this is the case. Here we can see Vi is applied at the negative terminal and plus terminal is grounded. So plus terminal is grounded means this is a inverting amplifier. But here we can see there is a feedback from the output to the input side. So this is a closed loop configuration. Open loop configuration can never be used as a amplifier because in open loop configuration, the voltage gain of the op-amp is infinite. Due to which if we apply any voltage, V1 minus V2 is 1 microvolt or V1 minus V2 is 2 volt, the output will get saturated, and that saturated voltage will be plus VCC, that is 15 volts supply. So in that case, we use the closed loop configuration in which some part of the output voltage is feedback to the input part, and this feedback is always given to the negative side. This feedback will never be to the positive side, because if we give the output feedback to the negative side, overall gain will be reduced, and this we can regulate the gain, because in open loop configuration gain was infinite, and that was a problem. So this problem is minimized here. We can control the gain by using RF and R1. So this is a closed loop configuration and inverting amplifier. Here we are understanding that what is the virtual ground. This point VA is the virtual ground, because the potential at this point VA is 0, but this point is not physically connected to the ground. So we know that the reasons of these, there are two reasons for this. First reason is voltage gain is infinite. Voltage gain is infinite. Voltage gain infinite means, like, if this voltage is V1 and this voltage is V2. So we can see V1 is equal to 0 and V2 is equal to VA. And we know that gain is equal to output upon V1 minus V2. So we know gain is infinite. So V1 minus V2 must be, for that case, V1 minus V2 must be 0. If the voltage gain is infinite, that this V1 minus V2 must be 0. So in that case, V1 must be equal to V2. So V1 is 0 and V2 is A. So we know that VA is equal to 0. That's why the potential at VA point is 0, and this point is called as the virtual ground. So one reason is this, and another reason is that ZIN is infinite. ZIN is the input impedance. This is the impedance between the two terminals, negative terminal and positive terminal. Input impedance of op-amp is infinite. So due to the infinite resistance, the current coming from this point, this current does not enter into the op-amp. There is no current flowing in this part. So the voltage drop across this ZIN remains 0. That's why the voltage at this terminal and this terminal becomes equal. That's why we can say that V1 is equal to V2 and VA is equal to 0. So this is how this VA is the virtual ground. Now we have to solve this question and we have to find the output voltage at this terminal. So we can see here minus terminal is grounded, and at plus terminal we are giving these voltages. So in this question it is given wrong, because there is a feedback always in the negative direction. There is no feedback in the positive direction. So this terminal will be negative and this terminal will be positive. This will be the correct. And now we can solve this. We can apply virtual ground concept. So the potential at this point is 0 and VA is the virtual ground. So VA must be equal to V1 and this will be equal to 0. So here current, we can find this current and this current, and no current will enter into op-amp. So all this current will pass through this resistance RF. So we can write the equations V1 minus VA upon 33 plus V2 minus VA upon 22 plus V3 minus VA upon 12 is equal to VA minus V0 upon RF. Now we can put the value of VA here. VA is 0 in each case, and V1 is given as 0.2, V2 is given as minus 0.5 and V3 is given as minus 0.8. So in this equation we will be having only one unknown, that is V0. So we can find the value of V0 here. So in this question we have to find the value of V2 and V3. So here we can see this circuit is for the unity gain follower. There is a unity feedback in the negative side. Feedback is always there in the negative side. In positive side there will be no feedback. So in negative terminal there is a unity feedback, and at positive terminal 0.2 volt is given. So this is the circuit for the unity gain follower, and in unity gain follower, output is equal to input. So it will, the output will be V1 would be, V0 would be equal to 0.2 volt. Now in this circuit we can see minus is there and the feedback is applied at the minus terminal, negative terminal. So it is correct, and output voltage is given to the positive terminal. So voltage is given to the positive terminal and negative terminal is grounded. So this is the non-inverting amplifier. So for non-inverting amplifier, the formula is 1 plus RF upon R1 multiplied by V0. So it will be, V0 means the input of this voltage is this V0, that is 0.2. So 1 plus 200 upon 10 multiplied by 0.2. So we can solve this and find the value of V3. Here we can see positive terminal is grounded and in negative terminal input is provided, that is the output of this unity gain follower, and that input is equal to 0.2 volt. So formula for this V2 is minus RF upon R1 Vi. So it will be minus 200 upon 20 multiplied by 0.2. So we can solve this and we'll have the value of output voltage V2. Now in this circuit, we can see this plus terminal is grounded and minus terminal is there. And here two resistors are connected with the negative terminal with supply plus 25 and minus 20. So this circuit is for the inverting adder. This is for the inverting adder. This is for the unity gain follower. This circuit is for the unity gain follower. And this circuit we can see plus is grounded and in minus terminal two resistors are there. So this is inverting adder. So here for inverting adder, what we can do? We apply here I1. We can find the value of I1. Here I2. And no current will enter here. So all the current will pass through this path. So this current is IF. So we can see I1 plus I2 is equal to IF. Okay. So we can find the value of I1 like 25 minus the potential at this terminal will be, due to the virtual ground, this terminal is grounded. So this will be VA would be equal to 0 due to the virtual ground. So 25 minus 0 upon 15 plus minus 20 minus 0 upon 30 and 0 minus V0 upon 600. V0 means like this one, V0 1. So in this way we can find the value of this V0 1, and this circuit, this is the unity gain follower. So here the output voltage will be minus 20 millivolt. Because the unity gain follower output voltage is equal to the input voltage, and input voltage at the positive terminal is minus 20 millivolt. So output will be minus 20 millivolt. Now this is also the inverting adder. So we can find this current, and the sum of current is equal to this. So V01 minus this, the potential at this terminal is, due to the virtual ground, it will be 0. So V01 minus 0 upon 30 plus minus 20 minus 0 upon 15 and 0 minus V0 upon 300. So in this way we can solve the value of, find the value of V0. Now next question is, the topic is the slew rate. So what is the slew rate? Slew rate is basically, it is the maximum rate of output voltage with respect to the unit step change in the input voltage. And slew rate, the unit of the slew rate is the volt per microsecond. Like we have this unity gain follower. And this Vi is equal to Vm sin omega t. So this V0 would also be Vm sin omega t. So how we can find the slew rate? Slew rate is the rate of the change of output voltage. So we can differentiate this dV naught upon dt, and this will be Vm W sin omega t will be cos omega t, and dV naught upon dt max, it will be maximum value of cos omega t is 1. So it will be omega Vm. So this is the slew rate, omega Vm. But omega is radian per second. So we can also write it as 2 pi Fs multiplied by Vm. Fs is the frequency in the hertz. So if we slew rate is also always expressed in volt per microsecond. So for expressing in volt per microsecond, we will divide it by 10 to the power 6, and then it will be volt per microsecond. This is the slew rate. Okay, so if we buy any IC, the slew rate of that IC is fixed. Like for IC 741, this is 0.5 volt per microsecond. Now, if there is a frequency, like I am applying input signal here, so and we want to this Vm is my 5 volt. So and the slew rate of that IC is 0.5 volt per second. So there will be a certain frequency of the signal that will be taking. Otherwise, that signal will be distorted. We are applying sine wave here, and in output there will be a triangular wave. So if we know the value of Vm and we know the value of slew rate, so we can find the value of the omega. We find the value of the Fs, and the frequency of that signal must not be greater than that Fs. Otherwise, that signal will be distorted. Like if we are having I am having the input signal like in this way. This is the square wave, and this is the 5 volts and 5 volt, and this time duration is 20 microseconds. This time duration is 10 microseconds. Okay, so we can see the slew rate is output changes per microsecond. It will reaches the 0.5 volt. So for reaching 5 volt, it will require the 10 microsecond. So this in 10 microsecond, we will find 10 microsecond is this. This is a 10 microsecond input signal, and this is the 10 microsecond input signal. Means we are applying this input signal is there 10 microsecond, time period is 20 microsecond is there input signal, and voltage is 5 volt. We are applying this signal to the op-amp, which is having the slew rate 0.5 volt per microsecond. So what will be the output waveform? So we can see according to the slew rate, the output of the op-amp reaches at 0.5 volt in 1 microsecond, and our input is 5 volt. So for the output to reach at 5 volt, it will require 10 microsecond. So in 10 microsecond, the output will be at 5 volt, and another microsecond it will be coming to the down. So we can see we are applying the square waveform, and at the output, due to the not the appropriate frequency of this signal, the output waveform becomes the triangular waveform. So that's why we have to choose the maximum frequency of the signal that we are applying at the op-amp, and this can be found by using this formula. Fs is equal to slew rate and Fs is equal to, we can cross multiply it by this, and we can find slew rate upon 2 pi Vm. So this is the formula for finding the maximum frequency that we can apply at the op-amp, so that the output must not be distorted. If we are applying the square wave at the input terminal, the output will be square wave also. So this is how we have this is the formula that I have derived in the last slide. And this is the question that we can find. Like in this question, for the signal, determine the maximum frequency that may be used here. So in the last slide, we have seen the maximum frequency we can found by using this formula. Slew rate formula was this Vm omega, and omega is your Vm 2 pi Fs. So this Fs will be slew rate upon 2 pi Vm. So we have to find the maximum frequency. So slew rate is given in the question 0.5 and Vm. We have to find the value of Vm, and Vm is for the output voltage. Here input is minus 0.2 volt and this is the inverting amplifier. So the value of Vm will be minus Rf upon R1 multiplied by Vi. So we can find 240 upon 10 multiplied by 0.02. So this V0 value, it will be equal to Vm. So we can apply the value of Vm from here. So this is the, so in this way we can find the maximum frequency of the signal. Here we can say this. We have found the value of minus Rf upon R1 mod 24. So 24 will become our Vm. This 0.48 will become Vm. Now the next is the CMRR. So CMRR is the common mode rejection ratio, and it is the ability of the op-amp to reject the common mode signal and to amplify the differential mode signal. So here we can see this CMRR is equal to ADM upon ACM. So CMRR is given in question A 100. So ADM will be 4000 upon ACM. So we can find the value of ACM here, and it will be 4000 upon 100, that is 40. Now VD will be equal to V1 minus V2, that is 150 minus 140, 10 microvolt, and VC is equal to V1 plus V2 by 2, that is 150 plus 140 by 2. So 290 by 2, that is 145 microvolt. And now we can find the output voltage, that is equal to VD multiplied by AD plus VC multiplied by AC. Now VD is given 10 microvolt, AD is given 4000, VC is given, VC is 145 and AC is given 40. Okay, so now we can solve this and answer will be in microvolt. So in next lecture, we will be discussing about the different applications of the closed loop configuration. Thank you.